If light has wave nature, it must exhibit the phenomenon of interference. When Huygens proposed the wave theory of light in 1678, there was no experimental proof for the interference of light. Subsequently, in 1801, Thomas Young demonstrated experimentally that light exhibits the phenomenon of interference. Let's carry about Young's double-slit experiment. Take an opaque screen with a small pinhole S and place a monochromatic light source to the left of the screen. Now, the pinhole S acts as a point source of light and propagates spherical light waves to the right of the screen in all directions. Place another opaque screen with two very closely separated pinholes, S1 and S2, to the right of the first screen. When S1 and S2 are illuminated by the incident light from S, they behave like two-point sources of light and emit spherical waves to the right of the screen. In fact, S1 and S2 behave like virtual coherent sources of light. These spherical waves from S1 and S2 can be made to interfere on the screen GG' placed in their path. They form a series of bright and dark bands called interference fringes on the screen. The bright band responds to constructive interference of light, and dark bands respond to destructive interference of light. Let's now study the interference pattern in detail. Let the distance between S1 and S2 be d, and the distance between the pinholes and the screen be d. Let AB be the perpendicular bisector of the line joining S1 and S2, and O be the intersection of the line and the screen. We shall now consider an arbitrary point P on the screen along the line GG' perpendicular to AB and passing through O. Let the distance OP be x. Light from the two sources S1 and S2 covers a distance of S1P and S2P respectively to reach the point P. If P corresponds to an interference maxima, then the path difference S2P minus S1P is equal to n lambda. Let us label this as equation 1. On the other hand, if P corresponds to an interference minima, the path difference S2P minus S1P is equal to n plus half lambda. Let us label this as equation 2. Here, lambda is the wavelength of light waves and n is an integer. From the diagram as shown, we can write that S2P square is equal to d square plus x plus d by 2 whole square. This is equal to d square plus x square plus d square by 4 plus xd. Similarly, S1P square is equal to d square plus x minus d by 2 whole square. This is equal to d square plus x square plus d square by 4 minus xd. Therefore, S2P square minus S1P square is equal to 2xd. This equation can also be written as S2P minus S1P is equal to 2xd by S2P plus S1P. If capital D is much greater than the small d, then we can assume that S2P plus S1P is approximately equal to 2d. Then the path difference S2p minus S1p is equal to x into d by d. Let us label this as equation 3. From equations 1 and 3, the condition for point P to correspond to a bright band is x into d by d is equal to n lambda, or x is equal to n lambda d by d. Let us label this as equation 4. From equations 2 and 3, if x d by d is equal to n plus half into lambda, then at point P, we will have a dark fringe. That is, for a dark fringe, x is equal to n plus half lambda into d by d. Let us label this as equation 5. Here, n is equal to 0, or plus or minus 1, or plus or minus 2, and so on. The distance between the centers of consecutive bright fringes or consecutive dark fringes is called the fringe width. If xn or xn plus 1 are the distances of the nth and n plus 1th bright or dark fringes from the central bright fringe, then mathematically fringe width is equal to xn plus 1 minus xn. From equation 4, the fringe width for a bright fringe can be written as lambda d by d. From equation 5, the fringe width for a dark fringe can also be written as lambda d by d. Hence, the fringe width is the same for both the dark and bright fringes, which means the dark and bright fringes are equally spaced. If the fringe width is represented by beta, then beta is equal to lambda d by d. Let us label this as equation 6. If the central point O is considered to be equidistant from both the sources S1 and S2, then S1O is equal to S2O. This condition corresponds to n equal to 0, condition for a bright fringe, and hence we will have a bright spot at O. Now, consider the line on screen that passes through the point O and this perpendicular to both the line AB and GG'. All the points on this line will be equidistant from S1 and S2, and hence we will have a bright central fringe along this line. On either side of this central bright fringe, we will have dark fringes. If n is taken as 0 in equation 5, we get the value of x equal to lambda d by 2d. Likewise, we will have alternate dark and bright fringes on either side of the central bright fringe. Note that a particular fringe corresponds to the locus of points with the constant path difference of S2p minus S1p. Mathematically, locus of such points represents a hyperbola. In fact, the fringe pattern is strictly a hyperbola. But for a large distance d, the fringes will be very nearly straight lines. Now, look at equation 6 again. The fringe width of any interference pattern is directly proportional to the wavelength of the interfering light waves. The fringe width is maximum for red light and minimum for violet light. The fringe width is inversely proportional to the distance d between the two sources S1 and S2. If we decrease the distance between the two sources, the fringe width increases. One more factor that influences the fringe pattern is the distance d between the sources and the screen. Fringe width is directly proportional to d. The actual separation between the fringes increases with the increase in distance of the screen from the two sources. Note that the angular separation of the fringes remains constant as the value of d changes. In the experiment discussed so far, the original point source S is assumed to be on the perpendicular bisector of the line joining S1 and S2, and the central bright fringe occurs at O. Let's now observe the changes that take place in the interference pattern when point source S is shifted with different position S'. Let point Q be the midpoint of S1 and S2, and the angle SQS' be phi. The central bright fringe is now shifted from O to O'. The location of O' is such that all the 3 points S', Q, and O' lie on a straight line, and angle SQS' is equal to angle OQO'. So far we have observed the interference pattern formed by light waves emitted by 2 point sources. All the fringes are straight lines, even though the waves from the sources are spherical in shape. If we add some more pairs of point sources horizontally, each pair of point sources form the interference pattern at the same location. Hence, the intensity of bright fringes increases. If the point sources are replaced with slits, a similar straight interference pattern is formed with increased intensity. What happens if we use 2 separate sources of light in place of S1 and S2? We don't observe any interference pattern on the screen. This is because the light waves coming out from 2 independent sources of light will not have any fixed phase relationship. Hence, they behave like incoherent light sources. We do not observe any interference pattern even when we use an ordinary monochromatic light source to illuminate both S1 and S2. The atoms in an ordinary light source radiate light in an unsynchronized and random phase relationship. Thomas Young has overcome this problem by using light waves from a single slit to illuminate S1 and S2. In this setup, any abrupt phase change of the source will reflect an exactly similar phase change in the light coming from S1 and S2. Since laser light is coherent, we observe interference pattern when S1 and S2 are illuminated by laser light.